So I'm Joseph Kotlarek. I did this work with the assistance of visiting professor I-Chen from National Taiwan University and my supervisor, Kwan-Liu. And this is a comparative evaluation of a couple different techniques that I developed with the lab to help users navigate virtual environments in a more productive manner so that we can send users into virtual spaces such as volume renderings or scientific visualization of any kind, and then they can gain the most out of it. So this started when we had data from the Princeton Particle Physics Laboratory that was very difficult for them to see. They asked us to visualize it. And we created a virtual fusion reactor based on ITER designs. And we built a whole environment where scientists could stand inside of this environment and see particles streaming around them. So it was fusion particle simulation data, and we helped scientists visualize the plasma as it moved around the reactor. And this was helpful for them, but it came to a few issues. And one of the big ones was that their spatial orientation, or the scientists' ability to remember where they'd been, where they currently are, and how that related to the data they were exploring, was lacking. They were unable to really effectively navigate through this data. So we worked on a couple different solutions to this, and this work is an evaluation of all of the best ideas that we had. So it starts with the main problem of these scientific visualizations, and which is common to a lot of scientific visualizations just beyond the particle simulation that we were looking at, which is that a lot of the time the environment is tied to the data. So in this case, we had a model of a fusion reactor that users were standing inside, and it's a massive space compared to the actual model that I'll show you in a minute. A human is just a little piece of it, and you can explore a massive area. So when users are trying to explore, we want to help them by providing environmental cues to tell them where they've been and where they're going. But it's difficult when the environment can't be changed without sacrificing the fidelity of the data or adding clutter to the environment or distracting the users in some way. So we came to a lot of different conclusions about how to fix this and what situations are best to use them in. And so I'll be talking about particle simulation data for the most part here, but most of what we learned is going to be similarly applicable to a lot of different kinds of scientific data, such as volumetric data and even abstract data, such as network visualization and virtual reality. So hopefully this video plays. Had some issue with this before. It looks like it will not. All right, so this is supposed to be a video, but we only see a still here of the actual particle data. And when you're standing inside this environment that we built, it's about 40 feet tall. So the user feels almost dwarfed inside of it. And you're able to see all these particles which leave their trajectory tails as they fly around, and you're able to experience the behavior of all the different particles and start to see trends in the data just by looking around. And we have some additional tools for investigating the data and getting a deeper understanding of it that I won't be able to show you right now. Oh, now it plays. Thanks. So the tokamak the Fusion Reactor is an interesting environment that we had a couple problems we needed to solve. First of all, it's radially symmetric. So this is an issue because when you're standing at any point in the environment, it's very difficult to tell whether you're at, if you're talking about like degrees rotation around the central axis, if you're at 0 degrees, 90 degrees, or any rotation around, it's pretty much impossible to tell, in fact. Additionally, it's non-oriented, so it doesn't really matter which direction is 0 degrees or 90 degrees, which will mean something later when I talk more about it. And then additionally, it lacks a ground surface, which seems kind of trivial, but it makes typical navigation techniques for VR much more difficult, because normally when you'd be using a point-and-click teleport or similar navigation technique, it relies on some kind of ground plane to keep you grounded so that you know how far you're going and you know where you can go. But we want users to be able to go up and down and explore this whole environment, which I said is about 40 feet from just on the inside. So we had to innovate a little bit when we're working with navigation in this space. So we have a couple different solutions here, and these three are the main ones that we investigate. Each one is kind of the culmination of a long-standing effort to improve certain aspects of the environment. And the first one I'll talk about is what I'll just be referring to as landmarks. And this constitutes adding pieces of, static objects, landmarks to an environment. And this is the image on the left, where we added markers such as north, northwest, northeast to the environment and allow users to see just where they are in relation to those static markers in the environment. The next technique is world in miniature or 3D minimap. I'll probably just call it 3D minimap. And this one is actually an attempt to show the user's position more dynamically. So it not only shows their position over time, but also lets them see a greater view, a third-person view of the environment. And then finally, we take a stab at improving the navigation overall. And this is a combination of several techniques, which I'll explore a little more after I talk about the rest in more detail. So landmarks, I talked about, each wall has its own marker, and these just let you see where you are. For instance, if you look at some data near the south marker, then you know that if you're now at the north marker, you're on the opposite side. And that's very simple, and it's hardly novel, but this does not come without its own drawbacks. The main one being that these actual directions have no meaning to the data because the data doesn't care what is north or south. And so we are always hesitant to add information that does not actually reflect the data because users may extrapolate that, oh, this was the north data, when it wasn't. It was just data that happened to be in the area that we marked north. So adding this kind of arbitrary landmark is not what we wanted to do, but something that was kind of our first approach in helping the users. Additionally, it's static, so it's very easy for users to learn and pick up, so requires almost no effort. And then moving on to the 3D minimap, users are able to point and click teleport, and every time they move, the minimap shows how they've moved with a yellow polyline. And this is just intended to help them see their history better. So users are able to clear the polyline so they can make a journey around the environment and see like, oh, I've seen this part and that part, and then clear it and start over. But this one has its own drawback, which is that it's a little more active. Users have to actively look at it to get any information from it, and it doesn't really provide the same just passive orientation that the others do. And then the waypoint navigation. And this is the closest thing to a novel technique that this paper presents. But it is still a close approximation to recent work by Habgood and colleagues to create a rapid continuous movement between user-defined nodes. So in this navigation technique, users are able to place these blue disks that you see that I'll call waypoints, and they're able to teleport anywhere as before just by pointing and clicking, but they also are able to more easily go back to places they've been that they deemed are important places to remember. So these waypoints are essentially a more dynamic approach to landmarks that don't provide arbitrary meaning because the users decide what's important. Additionally, this technique has a different kind of interpolation from getting from point to point instead of being instant from one frame to the next. When you choose to teleport somewhere, it will instead move you continuously there with an ease in and ease out animation, which helps users see just in a split second how they're traveling. And this was to combat a major issue that users complained about in the original design, which was that they did not believe or they had doubts that the teleporter actually took them to where they were aiming because of the nature of the environment not being completely clear about where you are. So to evaluate these three different techniques, we have an experiment with two tasks. The first is a navigation task. It's very simple. We simply asked users, and we had 21 users in total, to travel from a random position on one side of the environment to the exact opposite position of the environment. So this required users to be able to move around the environment and avoid the central pillar in the middle, which they could not move through. So it required multiple steps and keeping track of where you were as you traveled through the environment. And it wouldn't tell you when you got there. The users had to just know or figure out based on the environment cues when they had moved approximately 180 degrees around the environment. And we measured their time and accuracy in doing so. Additionally, the second task, dubbed the particle tour task, has users travel through the environment to touch some of the data that was randomly sampled from the original data set. In this one, there are always 8 particles that the user has to tap with their controller. And this is a challenge for users because they're supposed to touch all 8 of them, but they don't know which ones they've touched before unless they remember them. So this is a test of how well users can actually remember where they've been after going probably all the way around the environment and exploring it fully. Some of the techniques made this easier than others. From the experiment, we have some primary results, and we have a lot of findings that are in the paper, but I'm only going to go over a few of the more cogent ones here. And the first one I want to talk about is error. So For the navigation task, this was just the distance from the correct position, and for the particle tour task, this was the number of particles they missed out of the 8. And you can see here that in general, all of the techniques are better than nothing at all, with the exception of waypoints for the navigation task. It turns out that waypoints are not in fact useful for navigating the environment when you can't see the original waypoint you placed. So that was a common issue with that technique. When users placed a waypoint, they would then move away from it, and if they were trying to see where they've been, if there was something in between you, such as the central pillar in this environment, then it was not useful at all. So that was a major learning point for that technique, and it's a reason that it's not a very good one to implement on its own. It really needs something else with it. And then the next thing I want to talk about, and this is user feedback data. So we gave users a questionnaire, and we asked them to rate on a Likert scale of 1 to 7 the difficulty of each task with the environment, with the different techniques. And users typically preferred the minimap for the navigation task, which is, it makes sense because the minimap showed very clearly where you had started with the yellow line and where you had ended with the yellow line. And then for the particle tour task, it was a little bit flipped for the techniques. Each waypoint allowed you to very clearly mark which particles you had touched. So the ability for users to define what's important to them in the environment by placing waypoints was very useful. And landmarks performed well overall, but they were more generally applicable and not, they didn't have a niche use like the other two did. So I think the biggest takeaway from our user study, however, was just the sentiments that users had. So we had interviews with each user, and I've attempted to distill a lot of the sentiments into the most common phrases and such that were used. And this really, I think, sums up the advantages and drawbacks of each technique. Landmarks, of course, I've stated, were simple to use. They required almost no learning, but they added static pieces to the environment that users had nothing to do with, and sometimes that was distracting for users, and sometimes it took away from the data they were trying to look at. And then for the 3D minimap, users loved this one. It was exciting for them to see, and they enjoyed looking at their position as they moved around, and they liked being able to see the overall view, and it was just the user favorite. However, it did not necessarily perform better. We expect that a 3D minimap is very useful for most situations, but is best combined with one of the other techniques, such as landmarks or waypoints, to really get the most out of it and work in every situation. And again, the minimap actually slowed users down for the most case because they took time to look at it, and while this could be useful in some environments, it's not necessarily good for productivity if they're trying to get the most out of the data in a limited amount of time. And then with waypoints, users liked the improved quality of life that the ease in, ease out animation provided, but as for actually placing the waypoints, sometimes it was too much effort, and sometimes it was vulnerable to being blocked, such as with the navigation task that we had them do. So I'll conclude here with a couple learning points for each one. And this is essentially how each technique we tested can be used in the best situation, so that you can implement a VR environment and actually help users look at data in VR without losing all of their memory afterward. So for landmarks, it worked very well for quick experiences when you don't have time for learning. And again, it may sacrifice data fidelity. This is what I've talked about already. For 3D minimap, works the best for complex environments, just because when you're able to see a complex environment from the outside when you wouldn't normally be able to, then it provides a much better sense of where you fit into that environment that users would not otherwise have access to. But overall, it was the slowest, just because users took their time with it. And waypoints work well for open environments when you don't have occlusion, such as if you're moving through volume data, which has only transparent surfaces, or if you're moving just through an open room. But again, it performs very poorly when the waypoints are occluded, such that it is not useful at all. However, the quality of life provided with it is, such as the ease in, ease out, was very popular and surprisingly did not induce any VR sickness in any of the participants. Typically, that's something that is avoided in VR, is continuous movements, but with the ease in, ease out animation, it actually worked very well. And overall, I'd say the 3D minimap was the favorite. Everyone that participated in the study liked it the most. And it just is the most applicable to every environment without any real caveats that make it not applicable or not useful. So that concludes my presentation. I'll take any questions you have. Thank you.
Thanks, Joseph. So, are there any questions? Yeah.
Very interesting talk and application. The thing that I sort of noticed about your study design was that it was far simpler than the real data you showed earlier.
Right.
Have you deployed this now in the actual application, and which technique performed the best there?
So, unfortunately, we're no longer in contact with the scientists we originally did the study with, and experts are hard to come by. But for the most part, I don't have much information I can provide for you. I will say that if I were to finalize an implementation for this, I would use the minimap with the ease in, ease out animation, but I would leave out the waypoints and I would leave out the landmarks, just because in this environment, when you have thousands of particles streaming around, it's hard to see them anyway. It's not useful, and you really just want the minimap that follows your hand.
Thanks.
Thank you.
So maybe a follow-up to this one. I'm not an expert in Fusion Reactor, so you have to explain a bit so I assume the particles like flying around, and will they get some sort in a stable state after a couple of minutes, so that if you have a certain waypoint, that the particles will always behave in the same way at this waypoint, or will it be like randomly? Because in this case, you would need some sort of also not only give a spatial relation, but also temporal relation with every waypoint and landmark.
Right. So this data that we have here loops after about 3 minutes. So users in this environment, the way it was most commonly used was to stay in generally the same area for 3 minutes while you watched all of the data unfold, and then you might move and watch it from a different angle. And some of the tools that are also here that I didn't talk about much are the ability to look more in depth about what each particle is doing. You can highlight it so you can see its entire trajectory instead of the short one we show most of the time. And you can compare particles and look at their relative distances overall, and you can see their overall behaviors. Here in this slide, I have them highlighted with just simple colors, where each classification, red or blue, is a physics relation that each particle has. And in this case, the blue particles are trapped, the blue particles are passing, and the red particles are trapped. And this essentially says something about their behavior in the environment and how much they contribute to the overall electromagnetic field. Let's see. Is it playing? No.
Any other questions?
So when we really started this project, the task was just to see if it was fun to get hit in the face by particles. That was what we really wanted to know. But it turned out that this can actually be useful for scientists, even compared to a traditional two-dimensional display, because it's difficult to see the depth without this.
Wolfgang?
Not in the morning. So you're working in a very specific environment here, right?
Right.
Towards generalizing your results for different environments, do you have any insights there?
So I talk about these conclusions should be generally applicable. A lot of the techniques are going to vary in effectiveness per environment a lot. And in this case, I said that I would use a 3D minimap with part of the waypoints implementation. But in a situation where you're looking at, so I'm really only going to talk about scientific data visualization here, because that's really what my expertise is in and all of my experience is in. But if you're looking at a volume visualization such as voxel data, I don't have a slide here on it. I should have added a picture, but we have a supernova simulation where you can see transparent, essentially force fronts as a supernova unfolds. That is very interesting to stand inside, but again, it has a similar problem where there's not a lot of unique identifiers in the environment, where it's difficult to see where you are and where you've been, and this hurts users when they're trying to draw insight from it. So in that environment, I would definitely use waypoints, because landmarks don't make sense. There are no solid walls to attach them to. Again, the minimap doesn't make sense because there's no real physical object here. It's just a supernova. But the waypoints allow users to really decide what's important to them. And even beyond providing a spatial reference point, having users decide what's important to them can be very important for helping them remember.
I think that also gets extra points for the sentence, it's just a supernova.
It's just so maybe one more last question. Maybe Sebastian, you can already come up and plug in your computer. So I realized that in all the navigation aids that you gave, the means to get from A to B, you always use teleportation rather than real walking.
Right.
The scene itself didn't look like as it would be super big, so it looks like really like a walkable space, right? So what is like the mapping between the real physical space that you provided and the Fusion Reactor size?
The walkable space inside the reactor was about 400 square feet.
Okay.
Which is much bigger than our tracked space, at least in the room I was using. Potentially with the new base stations for the Vive, we could get a big enough tracked space for this. But trying to fit a small physical space into this environment would not work, because redirected walking or a similar technique would rely on users' inability to tell whether their perception has been altered in any way.
It's a nice curved,
Right.
so we have to talk afterwards.
Right. So.
Okay, so let's thank Joseph once more.